Hi and welcome to this tutorial series on graph basics. This video will introduce 3 famous graph traversal algorithms. Given the source and the destination, a path in the graph can be either the shortest or not. When shortest path is not a concern, the DFS algorithm is applied to acquire a good variety of results. If the purpose of query is to find the shortest path, in an unweighted graph, the BFS algorithm should be applied. While in a weighted graph, we should use Dijkstra. A concept always discussed along the shortest path is k-index of neighbor, which is defined based on how the shortest path is measured. In an unweighted graph, the shortest path is measured by the number of hops, and the k-index is defined as k-hop. In a weighted graph, where the shortest path is measured by the total weight of hops, the k-index is defined as k-weight or k-distance. Here, we arrange the nodes and edges of an unweighted graph in a hierarchical tree structure, of which the subject node is the root on top, and the rest of nodes are on the branches. Nodes from adjacent layers are in a parent-child relationship. This graph is not a tree in a strict sense of word, as there are networks resulting in one child with 2 parents and 2 brothers with connection. But it doesn't obscure the fact that the hierarchical layers in the tree correspond to the k-hop index, with the root being the subject node. This is better proved if we draw the graph in a k-hop target, where we put the root node on a bullseye and put the rest of nodes on the ring that matches the k-hop index of each node. Now let's discuss the first algorithm, DFS. DFS stands for Depth First Search. Starting from the root of tree, the DFS algorithm tends to explore to the nodes as deep as possible along the current branch before backtracking, until this is disturbed by the network structure of the graph and starts to explore to the nodes on the same depth of layer or even shallower. A DFS order hops back and forth between the tree layers. Let's see in detail how this is achieved. The data structure used to track the order of node traversal in the DFS algorithm is called stack. Initially, push the root into the stack. In a stack, always inspect the node at the far right whether it has one hop neighbor not in the stack yet. Frame up the node being inspected with a pointer, and find in the graph a hop from it where the edge and node are not traversed yet. Push the node into the stack. Now in the stack, Node B is on the far right. Suspend the inspection on Node A for the time being, and move on to inspect Node B. Explore from Node B. Move on to Node E. Node J has no neighbor not traversed, so it is exhausted. If we're programming, we should pop the exhausted nodes out of the stack. But in this demonstration, we keep it in the stack and mark it in gray color, so we can preserve the order of nodes being traversed. Now backtrack to the previous node in the stack to resume the inspection that is suspended. Node E also exhausts. Mark it gray and continue backtracking. Sometimes the untraversed edge may lead to nodes that are already in the stack, like the edge connecting A and D. Make sure not to duplicate those nodes in the stack. Now we have all the nodes in the stack. The remaining steps of this algorithm will backtrack to resume all the inspections suspended, but find all their nodes exhausted. List the k-hop index of each node in the stack. There's hardly any pattern of these k-hop indexes. A DFS order is subject to the priority of edges during traversal. Let's adjust the priority of edge and generate a different DFS order. This time, we explore the node C from the root. Still, it hops between layers back and forth. Compare these two DFS orders by checking the paths from the root to node G. Remember to skip the branches that are backtracked. The path on the left has 5 hops, while the one on the right has 2 hops. As we know that node G is on the second layer in the tree. It is a 2-hop neighbor of the root. We can conclude that the DFS algorithm can but do not guarantee to find the unweighted shortest path from the root to the node of our concern. In most of times, the DFS algorithm explores nodes through random paths. If we are only interested in the shortest path for whatever reason, we need to use BFS. BFS stands for Breadth First Search. It uses a different data structure to track the order of node traversal, which is called queue. Push the root into the queue and divide it as a zone, which is 0-hop. The queue always exhausts the node once it is inspected. So no backtrack is needed, and the pointer in the queue keeps moving forward to the right. Now this pointer is about to leave the 0-hop zone. Create a zone for the rest of nodes in the queue and mark them as 1-hop. Move the pointer to the right and continue the inspection. Node B, exhaust. Move the pointer to the right. Node C, exhaust. Similar with the stack, when edges lead to nodes that are already in the stack, make sure not to duplicate nodes. Now the pointer is about to leave the 1-hop zone. Create a 2-hop zone for the nodes on the right in a queue. All the nodes are in the queue now. The remaining steps of the algorithm will mark the last zone if not marked yet. As demonstrated, the BFS algorithm explores nodes neatly from treetop to down, layer after layer. Even though adjusting the priority of edge will probably generate a different BFS order, but it only shifts the order of nodes within each zone. The order of zones remains the same. As a result, the k-hop index of each node, the unweighted shortest path from the root to each node, can be retrieved. The last one to discuss in this lesson is Dijkstra. Dijkstra deals with the weight of edge when exploring nodes. It finds k-distance neighbors and the weighted shortest path from the subject node. Dijkstra also starts with pushing the root into the queue and divide it as a separate zone, but name the zone as 0 distance. First, it calculates the distances of all the neighbors from the root. The distance is the k-distance index of node A, which is 0, plus the weight of edge that leads to the neighbor. We elect node B and D that have the minimum value and push them into the queue. Now create a zone for these two nodes as one distance, which is the minimum value just calculated. Then instead of moving the pointer, we expand the scope of inspection. From all the nodes under inspection, explore one-hop neighbors with the shortest distance. Sometimes a neighbor may outstand multiple times with the shortest distance, like node F in the current election. This means multiple shortest paths exist for node F. Just make sure not to duplicate such node in the queue. An untraversed edge that leads to traverse the nodes, like the edge between node C and node G, will never contribute in the weighted shortest path from the subject node. Dijkstra is an advanced version of BFS. If we set all the weight of edge to 1 and run the Dijkstra algorithm, the process and result will be exactly the same as BFS algorithm. This is the summary of this lesson, and please follow our lessons in the future. We will show you more about algebra graph system and graph query.